So I think without further delay, I want to introduce you to Wouter. Wouter got his bachelor in the Hogeschool in Utrecht in 2010. And after that, he joined MercachemSyncom in the parallel synthesis group. He's been since then involved in the design and synthesis of libraries for multiple projects, including the European Lead Factory, where MercachemSyncom prepared 80,000 novel compounds. So it was during his search for novel scaffolds that he rediscovered electrochemistry, and he became an enthusiast after that. So I think now the word is for you, Wouter, and we're looking forward to your presentation.
Thank you, Elena, for this nice introduction. Thank you and welcome all to this presentation about the Shono oxidation and the synthesis of sp3-rich scaffolds. As Elena already nicely introduced me, I will only add that I have always been involved in experimenting, even as a kid, and I always was inspired by TV shows like The Mythbusters, for example. And I always liked this experimentalist approach and the pragmatic thoughts behind them to just apply the experimental data to new systems. So at MercachemSyncom, as Elena already mentioned, I started in the combinatorial department, first synthesizing the libraries for screening and hit finding and lead optimization. Eventually, I got into the synthesis part of the European Lead Factory. About 400,000 compounds were made during this cooperative effort, and for these designs of new scaffolds, we had to be creative ourselves. And for me, that was a very nice way to grow inside the company, but also to grow for myself. The design of scaffolds is a very creative process, and it involves a lot of chemistry and collecting a lot of knowledge on the way. Eventually, I even got more involved in the development of new or underexposed methodologies. And specifically, I've been more and more involved in electrochemistry since the last 5 years. So just to start, what are scaffolds exactly? Scaffolds are temporary structures that allow for the construction of final compounds using strict methodologies. Usually these molecules are small and can be orthogonically functionalized easily. As depicted below, I've got this example of a benzyl amine and an ester group that both can be deep protected and functionalized, yielding a nice library of compounds. So in the design of these new molecules, we try to aim at pharmaceutically relevant structures, of course, and they have to be novel, because it doesn't really make sense to create compounds that already have been made before. These compounds tend to be high in sp3 hybridization due to their inherent strong 3D character, which is better for probing proteins, but also allows for a lot of novelty inside the molecules. Me, myself, I like to be inspired by natural products, materials found in plants or in animals throughout the world, and they possess interesting features which interact in unusual ways with the body. So the design of these molecules is actually quite simple if you put it straightly. You can just draw any structure on the paper and everything is theoretically feasible, probably. However, I have found that this creative freedom was not always the best approach, and many of my routes that I proposed were immediate failures. Routes were too long, or either had a very difficult step at a non-strategic place in the route, or resulted in extremely low yields across the route, which was entirely unfeasible. So more and more I started appreciating a chemical toolbox that is a set of methodologies that I have experienced myself and have developed thoroughly, so I know the scope and the limits of these methods. such as if you have a grimy old toolbox containing a screwdriver and a hammer, I prefer to use those rather than some types of one-trick ponies that have to that require a lengthy training before you can actually see the use of it and only can use it for that specific goal. So a few of my favorite tools in this box are multi-component reactions, commonly known, of course, as the Ugi reaction, but for me, the most nice reaction I have developed in the past few months here is the Bargellini reaction. It's quite an old reaction using commercially available substrates. I get in a single step a highly functionalized scaffold. This way, I sometimes do not get great yields. Yields are generally between 20 and 50%, but because it's only a single step starting from simple materials, it's easy to scale up. It allows me for quick derivatization of these substrates. Another approach can be to use convergent routes, using starting materials that are quite easily converted to nice starting materials. For example, in this photocyclization reaction, in which an electron-rich and an electron-poor alkene are cycloadded to each other, forming this very nice bicyclic structure. There are many, many more tools in this set that I've developed in the past few years. But one of the most used, not entirely true, but one of the most explored types of chemistry is probably one of the N-acyl-iminium chemistry. It's not a field that I have been involved with for very long, but it is quite well known. And it generally relies on the leaving group and vicinal to an amide. For example, an alkoxy or hydroxy group is treated with a Brunstad or Lewis acidic reagent, eliminating the material, then forming an N-acyl-iminium ion, which is such a strong electrophile that nearly every electron-rich nucleophile can attack and form a nice molecule. These reactions can either proceed intramolecularly or intermolecularly. This powerful method has also been used for the production of many natural products, as I have depicted here from a chemical review. These are all extremely nice methods, and it has also been applied for the synthesis of tropanoids, which I will come back to later. And typically, these starting materials for the N-acyl-iminium chemistry are made using a variety of reactions. Specifically, the SpecAmp reduction is probably one of the most famous. It's the reduction of an activated amide or an imide and forming these materials. However, sometimes these starting materials are poorly available or require a lengthy synthesis, which strongly inhibits the usability of these reactions. And as a result, in the 70s, Tatsuya Shono introduced this reaction, which is an electrochemical transformation of an amide, a tertiary amide, to a hemiaminal. This reaction allows for the very quick diversification of commercially available substrates, which is incredibly nice, of course, as an addition to all those other possibilities of this chemistry. I don't want to say this is particularly the best reaction of all. It's just got a very different approach to it and can lead to a quick diversification rather than a highly specific diversification. So the Shono oxidation, it takes place through a double oxidation of this nitrogen carbon bond, and finally affording the N-acyl-iminium ion at the electrodes. This ion is such a strong electrophile that it reacts with methanol to form the methoxylated product. These methoxylated products are incredibly stable, quite stable, and they can be isolated, and once pure, or at least handled, they can be used in a variety of reactions using stronger reagents, for example, or in entirely different functionalizations on other positions as well. So I will try to go back in electrochemistry because not everybody will be familiar with it, and it's actually an ancient type of chemistry. It's very old. Even in the 18th century, Alessandro Volta in Italy already devised a method to create a current using copper and zinc electrodes in a battery. Later on, it has been explored more and more by people like Sir Humphrey Davy in the isolation of elements, and Michael Faraday, who devised many of the formulas that are currently still used for the electrolytic laws. Even organic chemistry has its first footsteps in electrolysis. Sorry, I need a sip of water. During this electrolysis of carboxylate salts, hydrocarbons are formed. However, due to the invention of reagent-based chemistry, it has been more and more obscured by those. This is due to a far more tangible approach. You can actually see the amount of material you're adding to your reaction. You don't have to measure anything, and you don't need specific dedicated equipment. And generally, electrochemistry is considered to be unpredictable or a type of black box chemistry. And how are you going to scale it? And eventually, because can you just increase the amount of electrodes, or do you need specific shapes, or do you need to do it in flow? And that's entirely contrasting to reagent-based chemistry, in which you can just add your reagent, see what happened, and then if it's not complete, just add more. On the other hand, electrochemistry can reach extremely high oxidation and reduction potentials, which can never be achieved using reagents, which are always bound to their own chemical limits. Reagents always inherently give byproducts, while electrons will leave no residue. And electricity is incredibly cheap and available, while reagents sometimes can be hard to source, and the price can be prohibitive for future or scale up. But one of the major things I would like to say about electrochemistry is that it just possesses entirely different reactivity compared to reagent-based chemistry. It's just a whole another field, and it cannot be exactly be compared to each other. So an electrolytic cell is a reactor containing always two electrodes, at least two electrodes. The positive electrode is an anode at which oxidation occurs, and the negative electrode is the cathode at which reductions occur. The choice of material for the electrode can be incredibly important because the reaction generally takes place at the surface of this electrode. One can imagine that the palladium electrode and the carbon electrode will have very different types of bonding to the molecule, thus reacting in a different way. The reactor itself can be divided or undivided, which my preference always is an undivided reactor due to their very simple nature. But a cell can be divided in an oxidative cell and a reductive cell, and that has been separated by a salt bridge or a electron permeable membrane. The problem with such divided cells is they are actually quite hard to scale. They require usually specialized glassware, or they even use specialized membranes that can be hard to source. For the rest of the cell will always be a solvent, an electrolyte, and a substrate. And specifically, the electrolyte will always be a very soluble ionic species. Sometimes this can be the substrate itself, but usually it's an additive that is inert and does not participate in the reaction itself. So in general, electrolysis or electricity should be considered similar to the flow of water, for example. A current is the flow or the amount of electrons that enter the reaction each second. And the voltage is the pressure or the power of the individual electrons themselves. It's the potential. Faraday's law states that the conversion rate is proportional to the current and time. And Ohm's law states that the potential and current are proportional to the resistivity of the cell, which is somewhat stable across different currents. Thus, simply put, increasing the current will increase the conversion rate. However, it will also increase the potential, which could lead to higher byproduct formation. Vice versa, decreasing the potential will always decrease the reaction rate due to a lower current in the cell. Eventually, you have added a certain amount of electrons to the cell, which is the total charge, which is depicted in the F of Faraday. Usually, these reactions do not proceed in 100% efficiency, much like normal reagent-based chemistry, and you just have to add an excess of Faraday. This is what we call the Faradaic efficiency. This is a nice way to depict the actual usefulness of a reaction. If anything has a Faradaic efficiency of only 5%, it just means you have to add approximately 20 times more energy to achieve a good conversion of the substrate. So it's all nice and well. Our very first experiments, we had no dedicated equipment at that point. I just had to try and devise a feasibility of this type of chemistry. So I salvaged a 5-volt DC phone charger from one of my old phones. I grabbed some graphite rods I found in an old battery in my attic, added some alligator clips, and electrolyzed my substrate in a beaker, specifically this Bock-protected morpholine. And surprisingly, although I had no idea what I was actually doing in the cell, I had absolutely no control over the current or the voltage in the cell. I had no idea which was limited. And I still got about 70% yield on several gram scale. However, when we tried to do some more learning, we found it had quite a difficult curve. We had no idea how to optimize, and at higher voltages we found that the electrodes just disintegrated, forming a nice layer of carbon on the bottom of the reaction mixture. Using the wrong salts or wrong substrates caused strong passivation, which led to a complete stop of the reaction. And eventually, when trying to scale it up, we found that cooling could be quite interesting, as essentially this reaction is not much different than an electric kettle. So at this point, this was not quite plug and play yet. Luckily, at around that time, ICA also introduced the Electrosyn. They developed this together with Phil Barron. Phil Barron is a great influence in organic chemistry, specifically in the electrochemistry field. And this machine has been made such that it's actually plug and play. You can do cyclic voltammetry quite easily with it to elucidate the actual oxidation potentials of your substrates. And you can set up your reaction parameters, such as the current, the voltage, or the amount of Faraday added to the reaction mixture. And this allowed us to actually optimize this reaction. So we first started with our standard system. We already found that methanol was a superb solvent, and electrode material, we found that graphite was far better than any other that we tried. We first tried to optimize the potential because we found that using different substrates, we got very different results. And at first we tried to do this all at 7 volts, which worked quite well for the Bock-protected morpholine. However, the CBZ protected morpholine, which is an entirely different group, of course, it is readily oxidized itself, forming benzyl alcohol, benzaldehydes, and benzoic acids in the reaction mixture. So many side products had formed. However, decreasing the potential to about 4 to 5 volts, we got very little side product formation, and actually a quite nice efficiency across various substrates. we found that although at 5 volts the efficiency drops somewhat for the CBZ group, the actual conversion rate almost doubled at this point. So we generally opted for the 5 volts, which was broadly applicable for all of our substrates actually. The electrolytes that we were testing with at first were sodium salts, which worked quite okay, but caused passivation when wrong substrates were used or wrong voltages, caused passivation of the electrodes and the drop in current. However, when you were using tetraethyl ammonium tosylate, which is an excellently soluble salt, we get a very nice current and still a relatively easy cleanup by just filtration over silica gel. We could increase the concentration of the electrolytes. However, we found that increasing the concentration did lead to a higher current, but to a significant drop in efficiency. This drop in efficiency was not great, as in you could double the amount of electrolyte, but you could lose more than half of your general efficiency in the reaction. So we generally opted for a 0.1 molar concentration of the electrolyte. And eventually we found that if we're doing reactions at a very low concentration, that the actual conversion was terrible. The efficiency dropped significantly at low concentrations. This was surprising. We did not expect this at this point. And then we tried to seek the upper limit of these substrates. And we found that even up to 2 molars, which is a very high concentration for normal organic chemistry, but we found that at these very high concentrations that the efficiency just kept on increasing actually. This was actually a very nice surprise, because it meant that combined with the 0.1 molar electrolyte in methanol, that we only have a catalytic amount of this electrolyte, which significantly increases or simplifies the purification of our substrates. Furthermore, graphite electrodes and around 4 to 5 volts was simply put the best conditions of this methodology. Now we were able to explore the scope of this reaction. We found that many activating groups are really suitable for this reaction as long as they are quite strongly electron withdrawing. We found that even non-amide type of activating groups such as cyanamide or tosylates are quite readily reactive, but the most superior reactions are simple amides and carbamates. Even substituted benzamides such as methoxybenzamides and fluorobenzamides react quite well in this reaction. We found that nicotinamyl amides did not react at all. There was very little conversion found, and this is thought to be that the pyridine ring just acts as a conductor for the electrons over the cell. The FMOC group was found to be quite unstable in this mixture, as well as very insoluble in methanol, which hindered the reaction in itself. So as one can see over here, there is a clear difference between different substrates, but in general, one can tell that all purple and pink depicted molecules react in a very clean fashion. Although efficiency of, for example, the tosylate group was only about 30%, just increasing the amount of charge applied to the cell leads to a complete conversion towards the desired material. And as depicted in white are the actual yields of products performed on a greater than 5 gram scale. And eventually we went to functional groups, in which we found that even quite reactive groups, such as methylene groups, aldehydes, alcohols, ketones, esters, they all work quite well. And we found that once the substrate was methoxylated, there was no further oxidation present in the cell. If we were able to actually dimethoxylate our substrates, but we needed an excess of over 40 faradays of charge to actually get some product. We also found that if the methoxy group is on a reactive position, such as this beta position to the ketone, that this could lead to elimination and further reactive species which react at the cells in the cell as well. And this resulted in a good conversion of the starting material, but an extremely low yield. And similarly to the pyridines, before we found that electron-rich substrates such as basic amines and phenoxy groups resulted in absolutely no conversion at all. These reactions also afforded very little side products, and the current generally just was a tad higher than having not these groups in the mixture. So suggesting that these also act as an electron bridge for the electrolytic cell. A nice example here in purple, all quite clean conversions, but specifically for quite hindered substrates, such as the 2-methyl ester that has been depicted at 70%. The original Faradaic efficiency observed was only 15%, which suggested that we needed about 14 Faradays for a complete conversion. But at large scale, we even had to use about 20 Faradays for a complete conversion to happen, because the reaction is not quite linearly, probably due to availability of the substrate. So eventually we did this on a very large scale. We did this on 0.3 moles, and we got about 70% yield of this 2-methyl ester product. Furthermore, we found that groups that are readily oxidized themselves or are known to reduce quite easily are not really suitable for the electrolytic cell. Although some products had been observed, we found that, for example, the nitro group was reduced to a nitrone, hydroxylamine, or even the amine. And the azide group itself formed adducts that we could not elucidate at all, and not the amide. Amines had formed. We also checked for different scopes, such as ring size, which just didn't really bother the reaction. Even acetidines formed nicely the methoxylated groups. We found that lactams worked well, and even ureas or acyclic substrates. Very hindered substrates, such as this diisopropyl amine, did not show any conversion at all. This is likely due to too much steric hindrance in the molecule. And in general, one can say that the regioselectivity of this reaction is quite good. It will generally methoxylate on the least hindered position, even if one were to expect that the benzyl group in this methyl benzyl amine would be the more conjugated type of substrate. It still provides about a 2-to-1 ratio of the methyl methoxylated product. Furthermore, the reaction prefers to react on the tertiary amide position rather than secondary amide position. This way we can get a very nice selectivity in the molecules. And then during this scope exploration, we had to increase the scale of some of these reactions, and we had this water-cooled batch reactor made using some simple carbon electrodes and a variable power supply that is generally not used on a chemical lab, but is still quite suitable, as one can just set a constant current or a constant voltage. And it translates quite well. For this 4-methyl ester piperidine, we found that at very small scale, at 1.5 millimole, we got only about 90% yield, and at large scale, at 100-fold scale, we found similar yields and similar purities. So now we have actually created a great methodology. We have shown that this reaction is not unpredictable anymore. It is actually quite predictable. It is quite scalable, and furthermore, it's very reproducible across various substrates. Although you sometimes have to add some more charge to the reaction, it still works quite well. So as a kid, I always liked these plasma globes, and using my finger to conduct this electricity and feeling powerful for some reason. And now at this point, I actually feel powerful that I can actually use the electricity in my reactions to make it do what I want it to do. So this is great for our future applications, of course. So some examples. It's quite simple to see how this methoxylation of molecules can be used throughout various simple starting materials that are either commercially available or made in only 1 or 2 steps. And it can be seen as a simple CH activation and can be used as such in the retrosynthetic pathways. So, for example, this tropane alkaloid has been made using the Shono oxidation in a double oxidation reaction and only the addition of an acetone to this molecule. And using that exact same principle, using one of our specific substrates, we can actually introduce a nice derivatization group in this tropanoid, creating a highly 3D scaffold using very simple methodologies. And furthermore, of course, this endothelial immunium chemistry has been researched quite thoroughly. It has been used for the production of actual drugs, such as tetrabenazine, and I can now easily make analogs of those. I can make natural product derivatives, or I can make unnatural amino acids for peptide synthesis. So to conclude, I would like to say that electrosynthesis is actually quite a unique and an incredibly useful technique that should be far more thoroughly explored. It's got a wide and diverse potential reactivity which has not been elucidated quite well yet. And my main takeaway from the experience of developing this chemistry is to have no fear to step outside of your comfort zone and try to look outside of your box and experiment away with any ideas that you have. And furthermore, for me, myself, one of the main things about this chemistry is just to enjoy the ride and do not try to despair for failed experiments, because failed experiments are just as useful or maybe even more useful than the successful experiments in your set. I would like to thank you all for your attention, and a special thanks to my students Alex and Elif, because they had done a lot of work for me. They had to do a lot of semi-random syntheses of ideas that I suddenly came up with, and they all did it for me. So thank you. I would like to ask you to direct the questions to Elena now.
Thanks, Wouter. It was a great talk, very informative, and I really like also how you play and make your own device to start using electrochemistry. I find this idea really, really cool, and I also really appreciate your comment about the negative experiments. We really learn a lot from them, and they are often neglected. But it's really true that we should consider them as important, even more important than the successful experiments. So now we have quite some questions, so we are going to start with that. Which is the standard workup method after the electrochemical methoxidation?
Okay, so for me, the standard way to do workup is just to transfer this reaction to a flask, evaporate the methanol, dilute the reaction mixture in ethyl acetate, and filter it over a silica gel plug. And generally, this elutes the product in a pure form, and the salts do not elute at all over silica. So this is very applicable and very. If it's really necessary, for example, for highly polar products that do not tend to elute in ethyl acetate, I found that a normal silica gel purification is quite feasible as well.
Okay. What is the order in which you optimize the reaction parameters? Do you start with electrolyte, current, concentration of reagents?
I actually just, considering the original attempts of us, we just started with a single literature thing that we found, using all sorts of standard parameters, and we found that this worked for us. And then trying to optimize, we at first found actually that the concentration of the substrate was far more dependent than the other variables. especially when doing research in organic chemistry, we tend to do reactions on a very low concentration, such as 0.1 molar or 0.2 molars. And instead, for a good reaction in this case, we always had to do this on a 0.5 molar. And it took some time to find this weird result.
Mm-hmm.
At first, we tried to optimize that. And then from that point on, we found that we could actually quite easily change all the other parameters. It's not a specific way to optimize for us at this point. We just use this same methodology each time again and again.
Mm-hmm. Yeah, that makes it more easy to, when you especially want to prepare several different scaffolds, that you have a method that you can apply to many different similar compounds. So Gabriela says, thanks for this interesting presentation. Thank you, Gabriela. Well, on behalf of Wouter, can you comment on the reaction time needed on average to reach good conversions? And do you need longer reaction times upon scale up?
That's actually very nice. So the contact area of the electrode, of course, dictates the amount of current that could flow through the cell. So you could say that increasing the amount of area would lead to an increase in current, thus having a higher reaction rate. And generally, for a typical reaction, I could say that 2 Faradays on our large scale could take about, I believe, 14 hours or something like that. So it's about 100 or 150 millimolar. It really depends, of course, on the current of the cell, which can vary quite a lot through various substrates. If I were to do this reaction that I had to do on 20 Faraday, for example, that took quite some time. It took me 4 days. But on the other hand, it took me 4 days, and the only thing I had to do was sometimes refill the methanol that evaporated or reacted with the electrodes.
Mm-hmm. Okay. Yeah, maybe it's a little bit related to the next question. How safe would you say is electrochemistry? So you have it running overnight or over a few days without any problem?
So I think electrochemistry is relatively safe. It does evolve some hydrogen gas and possibly oxygen gas or formaldehyde in this case. CO2 can evolve. Of course, you have to get rid of these gases, and I wouldn't use an enclosed space. However, on the electricity side of the chemistry, I would say it's very safe. The currents and voltages I use are far less than a 9-volt battery, for example, can produce. It's only a few watts of power that I use for our large-scale reactions, and it's just it wouldn't pass the skin at this point of your hand. And then again, you're probably using gloves, so it wouldn't penetrate you anyway. Okay,
thanks. Have you tried doing constant current reaction? Did you optimize any electrolysis reactions using cyclic voltammetry?
So first, cyclic voltammetry is very nice to find the actual oxidation potential of my molecules. However, I found that the actual oxidation potential is around 1.8 to 2.5 volts, which is far lower than the actual voltage that I'm using. This is mainly because at those voltages I only get an extremely low current due to being absorbed completely by the substrate. So an overpotential is generally considered to be best practice for electrochemistry. However, then again, you have to take in mind that that could lead to side product formation. During the optimization of the reactions, we usually used a constant voltage because the electrosyn itself calculates the amount of charge applied to the reaction. So you would have the same potential, so you would expect very little changes in side product formation, and then just calculate the amount of total charge based on the resulting current. If you were to use a constant current for the optimization, then you could have a fluctuating potential, which could lead to various product formations over time. And especially if the reaction takes overnight, I can't actually observe the fluctuations in the voltage and act upon that.
Okay, Thanks. Alan says, very nice talk. Thank you, Alan. And do you see any reactivity at secondary amide site? You had a cyclid example versus tertiary amide sites.
For linear groups, I guess this would be. I have not tested that thoroughly yet for this reaction. However, I have found that if you were to continue the reaction beyond the first methoxylation, then eventually you will get further methoxylation of the secondary amide group. So yields generally tend to be a bit lower, of course, but there is a high preference for the tertiary amide groups at all times.
Okay. Thanks. So you said that increasing the charge Faraday increases reaction rate, but also byproduct formation or side reactions. Do these byproducts appear simultaneously with your desired product or over time? For example, does your desired product react further? What are the most common side reactions?
Increasing the current increases the reaction time, and increasing the total charge leads to a more complete conversion due to the non-linearity of this reaction rate. Regarding the second question, could you please read?
So the first question was if these byproducts appear simultaneously or they are coming from the product. And the second question is, what are the most common side reactions?
Yeah, so the main side reactions that form that I have not actually been able to elucidate quite well because they tend to remain at the silica gel baseline. So I would expect these to be mainly polymerization products. For some substrates, for example, for the tosylate morpholine that we tested, we found that elimination of the methoxy group was a quite common side reaction as well. This could also interfere with the follow-up chemistry, of course. Mm-hmm. Regarding the simultaneous formation of these side products, I could not really comment on it because it really depends on your substrate. Sometimes the methoxy group is incredibly stable, and the only side product we observed was the second methoxylation at only a few %. However, at some other substrates, for example, we had the 3-methyl piperidine substrate, and we found that we had, of course, reduced selectivity between the 1 and the 2 and the 6 position of the molecule, and the 2 position tended to eliminate towards the methyl ester. This resulted, of course, in itself to be oxidized and reduced and then form other molecules from that. But we have not actually sought to find out what happened to those molecules. Generally, we are only focused on the methoxylation of the molecules, and the side product formation is just regarded as waste at this point because it's not a major product that has formed.
Mm-hmm. So Guido has a question that I actually also have myself. So thanks, Guido, for asking that. There are recent studies about the use of flow chemistry for electrochemical reactions. What is your opinion about this approach?
Yeah, flow chemistry can be applied quite well, I think. And I have prepared a slide regarding this. So the group of Timothy Noel in Eindhoven has been using this exact reaction in flow in a biphasic system in which the methyl carbamate of pyrrolidine is oxidized in one side of the biphasic system, then diffuses to the other layer and reacts with the allyl TMS that is present in that phase. This is a very nice idea, of course, for a scale-up of reactions, and I would assume that it is perfectly capable to produce kilogram quantities of material this way. If I were to look into chemistry devised by Phil Barron itself, so I have, it's a bit higher up. So this chemistry here below is a birch reduction devised by the group of Phil Barron, which they have been doing in a flow cell themselves, which is a very nice application of flow chemistry for electrochemistry. Chemistry. It's chemistry that is usually done batch-wise because it's so incredibly difficult to control using sodium amide in ammonia, for example. So definitely, flow chemistry is definitely feasible for electrochemistry, and I would say that Shono oxidation in itself is useful. It can be quite useful as well, because the only thing that you need is two electrodes and the flow of your material through it, and you can actually get a huge surface area compared to the amount of material, thus increasing the reaction rate. Yeah, definitely.
So something to try in the future. Next question is, would other solvents be suitable for this reaction?
Yeah, so systems that have been utilizing acetonitrile water can be used, creating the hydroxy group. Ethanol and isopropanol have been used as well as substrates. However, using those other systems, you will get, for example, a reduction in current, or the product formation is slower due to being poor in nucleophiles, or in the case of a hydroxy group, they are far more reactive than the methoxylated species, thus resulting possibly in other byproduct formations. Mm-hmm. But yeah, other solvents are definitely useful. Especially one to mention, here on the bottom right, we have found that even in the presence of a significant amount, in about 10 equivalents of DMF in the reaction mixture, we found a high selectivity towards the cycle methoxylation versus the methoxylation of the DMF, which is something we have not been able to explain yet, but is quite interesting as well.
Mm-hmm. Nice, thank you. The next question I find quite interesting, because I think this is what many people feel before starting these new technologies in the lab, such as electrochemistry and or flow, for example. So how long does it take to optimize a reaction? And is it worth compared to a more traditional approach?
Yeah, but for me, the optimization always was just a matter of a few hours.
Okay.
So we have actually quite small vials for the Electrosyn at about 2 to 3 milliliters. And if you have only a 0.5 molar concentration and quite high current, then you can have a good conversion in around 2 to 3 hours. We also found that you do actually need complete conversion to tell a lot about the reaction. The only things that you have to look at is byproduct or side product formation. So trying to optimize it is not always actually isolating this material, but just trying to suppress the side product formation. So even at reaction times of about 1 hour per optimization step, I can try to optimize it quite readily. Sometimes we had optimized the reaction using this methodology we devised in just a couple of hours. Okay. Usually these conditions are broadly applicable for many substrates.
Mm-hmm. So I guess once you get more used to the equipment and so on, then you can be really fast. Of course, it always takes a little bit to get acquainted with a new concept, maybe that is different from a normal or a traditional reagent approach. But I think you did a very great introduction for that. So I think that should be also very helpful. So we have more questions. Let me see. Have you looked at other reactions?
Yeah. So I already showed this. Oh, sorry, I need to click this one. I already showed these. And I can also show this one. We actually originally we tried doing this the first electrochemical reactions with the Electrosyn using the trying to do the Kolbe electrolysis. We found this to be a potential nice way to introduce a high variation in the molecule, because carboxylic acids are very useful. However, we found that this reaction is incredibly difficult to achieve. And I actually asked Phil Barron himself, and he said the Kolbe reaction has its dirty little secrets. And I
okay.
The products that we found were indeed decarboxylation, but then hydrogen abstraction of the solvent. So this was a very difficult reaction, and we could only use it for a few examples. And then I found myself trying to decarboxylate an amino acid, which was quite difficult actually for this specific molecule because it contained several very reactive groups, and I had no idea how to achieve this. So I tried to do this electrochemically, and surprise, surprise, I had about a 50 to 60% yield using just a large scale, and I actually did this reaction on 500 grams of final scaffold. And eventually, I even tried to do some other reactions, such as this birch reduction that I already passed by earlier, and this works very well for different reductive systems as well, and was the inspiration of further optimization. Eventually, I did not have to use the electrochemical system anymore, but it was still a very nice starting point using the plug-and-play system that we had in place. And I also used this sulfonate oxidation towards the trifluoromethylation and ring expansion of allyl alcohols, which worked actually quite well as well. So there has been beautiful chemistry reported, and it's actually quite easily set up as well.
Yeah. Nice, thank you. Well, we cannot reach in the end of our time, and thank you so much, Wouter, for this presentation and for the Q&A session. It was really great. There's two things I want to say before leaving. We will be having another session today. We will be going live at 6 again for this webinar. So if you have friends that couldn't join in the morning session, please let them know, because we will be we'll be live presenting the webinar and answering your questions. And as I mentioned, we will be continuing with the webinars. So the next one will be on September the 8th, and we will have Martin Strack talking about route scouting for kilogram scale manufacturing of active pharmaceutical ingredients. So also one not to miss. So thank you so much, everyone, for joining us today, and we'll see you later today or next month. Bye.
Bye.